Guys, welcome to my YouTube channel Learning Biophysics with Team 320. My name is Abhishek Sharma and today's our topic is physics of enzyme-substrate interactions. So the interaction between an enzyme and its substrate is a complex process involving various physical forces and principles. These interactions are essential for catalysis. The process by which enzymes accelerate are the chemical reactions are first is electrostatic interactions. In the ionic interactions is the attraction between oppositely charged groups on the enzyme and substrate, and the hydrogen bonding is weak electrostatic attraction between a hydrogen atom and bond to a highly electronegative atom such as oxygen or nitrogen and another electronegative atom. So van der Waals forces are weak in attractive forces between a molecule arising from temporary fluctuations in electron density. The second one is hydrophobic interactions. So non-polar interactions are the attraction between non-polar groups on the enzyme and substrate. And the hydrophobic effect are the tendency of non-polar molecules to aggregate in water, driven by minimization of unfavorable interactions with the water molecules. The third one is covalent interactions that in the temporary covalent bonds. In some cases, enzymes form transient covalent bonds with their substrate during the catalytic process. Some substrate complex are these covalent interactions are contribute to the formation of enzyme substrate process complexes. The enzyme substrate complex formation is by the three process. First one is a log and key model. The model process that the enzyme and substrate fit together like a log and key. So with a precise complementary shape. Okay, and the second one is induced fit model. The model suggests that the binding of the substrate induces a conformation change in the enzyme leading to a more complementary fit. The third one is transition state stabilization. So enzyme lower the activation energy of a reaction by stabilize the transition state and intermediate state between reactants and products. The factors affecting enzyme substrate reactions are the substrate constant concentration. It's the rate of enzyme catalyzed reaction generally increase with an increase substrate concentration with until a saturation point is reached. The second one is pH. Enzyme have optimal pH values at which they function most efficiently. Derives from optimal pH can disrupt an enzyme substrate interactions. The third one is temperature. Enzymes have optimal temperatures for activity. Excessive temperatures can denature or degrade the enzymes and they're disrupting its structure and function. The fourth one is inhibitors. Inhibitors can bind to enzymes and interfere with their ability to bind to substrate, reaching the rate of reaction. Okay, guys, thank you. So my second video is about electronic conformational interactions in enzymes. So these interactions plays a crucial role in the catalytic activity and regulation of enzymes. These interactions involve interplay between electronic properties and conformational changes within the enzyme molecule. Key aspects of electronic conformational interactions are: first one is electron density distribution. The distribution of electron density within the enzyme molecule influence the overall shape and conformation. The also changes in electron density can lead to conformational changes affecting the binding of substrate and the catalytic process. The second one is charge distribution. The charge distribution of charges within the enzyme molecule is important for electrostatic interactions with substrate and cofactors. Changes in charge distribution can influence the enzyme affinity or for substrate and its catalytic activity. The third one is conformational changes. The conformational changes are the binding of substrate or effector molecules can induce conformational changes in the enzyme. These conformational changes can alter the electron density distribution and charge distribution within the enzyme, affecting the catalytic activity and regulation. The fourth one is allostatic regulation. Electron conformational interactions are essential for allosteric regulation, where the binding of a molecule at one site affects the activity of the enzyme at a different site. Changes in electron density or charge distribution at the regulatory site and induce conformational changes that alter the catalytic activity at the active site. The examples of electronic conformational interactions in enzymes are: the first one is hemoglobin. The binding of oxygen on one heme group induces a conformational changes that increase the affinity of the other heme group for the oxygen. This is an example of positive cooperativity driven by electronic conformational interactions. Second one is aspartate transcarbamylase (ATC), with the binding of allosteric activator ATP to ATC induces a conformational change that increases the enzyme's affinity for its substrate aspartate. This is another example of positive cooperativity mediated by electronic conformational interactions and conformational interactions. Techniques for studying electronic conformational interactions are like first one is X-ray crystallography. This technique provides high resolution structure of enzymes, allowing the analysis of electron density distribution and conformational changes. Second one is nuclear magnetic resonance (NMR) spectroscopy. NMR can be used to study the dynamics of enzyme molecules and to probe electronic properties. The third one is a computational methods. It's a molecular dynamic stimulation and quantum mechanical calculation can provide insights into electronic conformational interactions. So, guys, thank you.